Hello, uh, I'm Karan from EPH branch, and today I'm here to present. And the topic of my presentation is sampling of the signal. Right. So the topics which we are going to discuss today are what is sampling and its important terms, sampling theorem, aliasing effects, signal sampling techniques, Nyquist rates, and application of sampling techniques. What is sampling in signal processing? In signal processing, sampling is the reduction of a continuous time signal to a discrete time signal. Sample is a piece of data taken from the whole data. And the common example is the conversion of a sound wave in a continuous signal to a sequence of samples, a discrete time signal. This is an example of how sampling can be represented. This is as you can see, this is a continuous signal, and we take some points after a fixed intervals, and on these fixed intervals we find the amplitude of our signal wave, and then we convert that into discrete waveform. What is the sampling rate? To discrete signal, the gaps between the samples should be fixed, and this gap is known as the sampling rate. And sampling frequency is the reciprocal of the sampling period. The sampling frequency can also be represented as sampling rate. Now, what is signal sampling theorem? So a continuous time signal can be represented in its samples and can be recovered back when the sampling frequency is greater than or equal to twice the highest frequency component of the message signal, right? Like that is, the sampling frequency fs should be greater than or equal to twice the highest frequency component of the signal. Now here's an explanation of how sampling theorem works. So we have a continuous time signal right here, and you multiply it with the impulse signal, and you get output signal. Here is the impulse signal delta t, and it is taken on a particular event which is ts, and when you multiply it with the input signal, you get this discrete sampled signal, and it can be represented in its frequency domain by x omega, and the output can be represented by y omega. As you can see, the y omega is in the form of period discrete form, and it can also be recovered back to its original signal. Now there are three various modes in which sampling can be done. This is an example of oversampling, in which you can see that the output wave is not continuous. There are certain gaps in between the output signal, and this is perfect sampling, in which fs, the sampling frequency, is equal to twice of the maximum sampled input signal, and you can see that there is no gap in between. And this is undersampling, in which you can see that there is an overlapping. Now what is aliasing effect? The overlapped region in case of undersampling can be represented by aliasing effect, and this aliasing effect can be removed by considering fs is greater than or equal to 2m, or by using anti-aliasing filters. Now what are the various signal sampling techniques? There are mainly three types of signal sampling techniques: the impulse sampling, the natural sampling, and the flat top sampling. Now what is impulse sampling? Impulse sampling, as the name suggests, that we use an impulse train and we multiply it with the input signal, and we get the output in the form of an impulse train, in which the magnitude of each impulse is represented by the magnitude of the input signal. This is also known as perfect sampling, but it is not done practically because we can't obtain almost perfect impulse signal, and also the width of the impulse signal should never be equal to 0, which in case you can see that the width of the impulse signal is 0, but in practical world we do not have impulse signals with zero width. The next is the natural sampling, in which the same impulse signal, the same input signal is multiplied by a pulse train instead of an impulse train. The pulse train has a fixed time period of t and has a certain width. And as you can see, it has a fixed magnitude, and it has a fixed time frequency, and it has a fixed width. And the output is represented by this wave, in which you can see that the amplitude of at each certain point has some noise on the top, and this noise can be neglected by using the flat top sampling. In flat top sampling, they use the same pulse train and the same input, but in this we have a fixed magnitude for a fixed time point. We do not have any kind of noise over there, and this is the most used sampling technique. Next, we have the Nyquist rate, and Nyquist rate is the minimum sampling rate at which the signal can be converted into samples and can be converted back without distortion, right? So for a Nyquist rate, the frequency of the Nyquist frequency is equal to the 2 times the maximum frequency, and the Nyquist interval is the reciprocal of the Nyquist rate, which is 1 divided by 2fm, right? Next, we have the applications of sampling theorem. So there are a few applications of sampling theorem which I have mentioned here. As you can see, sampling theorem can be used to maintain sound quality in music recordings. Sampling processes applications in the conversion of analog to discrete form, as you can see. Sampling recognition system and pattern recognition system. Sampling is also used in modulation and demodulation, in sensor data evaluation system, in radio navigation system. Sampling is applicable, and sampling, digital watermarking and biometric identification systems and surveillance systems. These are the fields in which we can use the sampling theorem. So this was it. Thank you for listening, and bye.